fifth place winner in ISIC competition will start the presentation. Today, I'm excited to share with you the solution that helped our team achieve fifth place in the 3D TBP for skin cancer detection competition. This is the agenda of today. Uh, our team consists of 4 members. Outson played a crucial role in researching past competition data and improving the Tabia model's performance. Hattori-san focused on image model development and successfully achieved very high accuracy classification using an image model with auxiliary loss. Fukuyama-san mainly focused on tabular model development and ensembling our models. The final model configuration for the entire team was done by him. Finally, Nagatsuma, I developed both image and tabular models and contributed to the diversity of the models to ensemble. By leveraging each member's expertise, we collaborated effectively and were able to rank fifth out of 2,740 teams, earning a gold medal. The task we tackled in this competition was to develop a machine learning model to assist in the early detection of skin cancer, specifically melanoma. This challenge involved analyzing images from 3D TBP, which captures detailed full body images of the skin to identify suspicious lesions. We are also given tabular metadata as supplemental information. Our team took on these challenges and approached the problem in an efficient way, which I'll be explaining in detail throughout this presentation. In the end, we finished fifth and won gold medal. I'm looking forward to walking you through our solution and the key steps that led to our success. In the tabular model using metadata, we found that several features were important. There were 3 main points: features related to age, features representing the size and shape of the tumor, and aggregated feature engineering. It was an average to realize early on that aggregate features were particularly important. The age of the patient emerged as the most important feature in our analysis. There were cases where multiple ages appeared in the same patient ID. In these cases, there were only a few data points for younger ages, and they were often positive. Although it may not have been an essential detection power, the age feature was essential to reflect this trend in the prediction, and it contributed greatly to the accuracy. The variable representing tumor size ranked highly in feature importance. Positive tumors seem to have a wider distribution of sizes than negative tumors. Since we only used it as a single numeric feature, it did not differentiate us from our other teams. However, it was an intuitive result that tumor size is important in determining pathology. Aggregated features by patient and tumor site are not often used in public notebooks and were effective in improving accuracy. I think it was necessary to realize the importance of these features in order to rank highly in this competition. Feature groupings were used by patients, tumor sites, and medical institutions. For each grouping, we aggregated the mean, variance, and normalized value of numeric columns to create features. We adapted a cross-validation strategy to evaluate accuracy offline and improve model. The division of the training data in cross-validation was common within the team so that we could ensemble the results in each fold and compare accuracy. Since the test data and training data did not have patients in common, it was necessary to group the same patients so that they were included in the same fold. Um, Now I would like to introduce the first image model developed by Nagatsuma. A key feature of this model was resampling negative samples at the end of every epoch, which allowed for more diverse training data throughout the process. On average, each epoch took around only 10 seconds to complete. For training, I leveraged Google Cloud Pro with an A100 GPU, training for 30 epochs in total without any early stopping. In terms of model architecture, I experimented with several backbone models from the team library, known for its efficient deep learning models. For inference, I trained one model on the full dataset, which not only reduced inference time but also achieved performance that was comparable to or even slightly better than using the traditional five-fold models. The efficiency of the model increased the number of potential possible ensemble patterns. I also conducted five-fold training mainly for stacking purposes and for calculating validation scores. Next one is image model 2. Um, First, let me explain the features of this model. Unlike the previous image model, we did not use any downsampling. We used all the data, including past competition data. Since the dataset is large, we trained for only 5 epochs and did not use early stopping. Next, we introduced an auxiliary loss. There are two important factors here: whether the data has a ration ID or not. Images with a target of 1 always had a ration ID, and there were many has ration ID equals to 1 images. Whether the data is from past competitions or not. By using these two auxiliary losses, we improved the CV score of the single model from 0.125 to 0.151. Uh, for the model backbone, we use a team library with several models, including CompNext Small, ResNet 18, ResNet 152, and Swing Small. During inference, we randomly used 2 out of 5 false models for each batch. This helped reduce inference time compared to using all 5 full models. Finally, the scores are as follows. CV score is 0.167, public score is 0.162, and public score is 0.152. Next one is Sabia Model 1. This model was created with a relatively simple configuration. Originally, I was used a model that had been steadily improving since the beginning of the competition, but I suspected that it was overfitting to both CB and LB, so I re-examined my previous ideas and created a simple model. Many of the features are aggregated features obtained by several groupings. I did not use the image model prediction value as GBDD input because a simple ensemble gave better accuracy than stacking with the image model prediction value as input. Next one is tabular model 2. In tabular model 2 part, we created around 3,000 features. We applied several aggregation granularities, for example, not only grouped by patient ID, LV location, but also include attribution, tile type, and also created shift features, which treated past patients' ration information as a feature. Training with past metadata, some patients exist both previous competition and this competition. We used this information. And we applied soft labels, treated intermediate samples as target 1, sample weight 0.5. This led to smooth training process. In feature selection part, 0 important features across all 4 was dropped, and we use YGBM and XGBoost. This is Tabia Model 3. In Tabia Model 3 part, we created around 600 features. No significant difference from Tabia Part 2 in features, but less aggregation patterns. This model used data from past competitions to increase the positive sample. This was done in the hope that increasing the positive sample would improve the running process. Tuning the scale post weight parameter of light GBM improves the accuracy, and we use light GBM and XGBoost. In ensemble part, we applied weighted average by UpTuner. When we use several image OLF, we choose diverse backbones. For example, swing base, connext base, ResNet base. To avoid overfitting, we also tried sample rank average without weighting, but worsened the private score. We needed to improve the model while checking both the CV and LV scores. The correlation between the scores was not very stable, which we thought was because the test data included unknown hospitals. We noticed this towards the end of the competition, but the seventh team seemed to have noticed the problem earlier and dealt with it well. Both Phoebe and LB had few positive examples, and LB in particular was at risk of overfitting. However, we had to refer to the LB score to see how it performed on unknown hospitals. Forcing the CV was a way to improve the model's performance, but there was a risk of overfitting on known hospitals. In the end, Fukuyama-san made the decision on the ensemble with more emphasis on CV, and it turned out to be successful. The simple model configuration with high accuracy was to pass the predicted value from the image model to the tabular model as a single feature. It seemed that many of the top-ranked solutions had a pipeline with this configuration, and with some original ways to increase diversity of models. It is difficult to achieve a level of accuracy that would rank highly with this simple configuration, but in practical terms, it may be better to use this simple configuration. Overall, I think the key to winning this competition was how to improve generalization performance while avoiding overfitting. In a situation like this, one where there are few positive examples, overfitting to CV and LV can easily occur. There were big shakes in the private LV, and public LV from the middle of the competition onward was not very helpful. In order to increase accuracy while reducing the risk of overfitting, I think the most important thing was to create multiple prediction pipelines to acquire model diversity and ensemble them. Thank you for thank you all for your attention. I am excited about the potential of our solution to impact skin cancer detection positively. Uh, Sorry for my poor English. That's all. Thank you.